Hey guys, this is Mr. Galoya here. We're back on this graphing packet. We already did the direct or linear relationship, and now we're on page 2. And this is maybe the second type of graph we see pretty common in physics. This is called an indirect relationship. Some books or math teachers will call this an inverse relationship. And if you kind of look at the data here, as one of the column goes up, the other one kind of goes down, and that's kind of what you see with an inverse relationship. Here's the sentence: my other son Ryan takes the same car and changes the mass of the car. So basically he's making the car heavier. He then gives it a push and measures the force from his push. Well, if the car, does it make sense? If the car is kind of lighter, then his push results in a bigger force that acts against the card. So as the card gets heavier, his kind of push results in less of a force being imparted to the card. So there's the data. Again, he makes this change, so that would be our independent variable, and our force then represents our dependent variable. So we got kind of a blank graph here. Notice we've got a couple of different graphs here. We're going to use the top one, and we're going to use the bottom one here shortly. We've got this independent variable will be on the x-axis, and that independent variable then represents the mass in kilograms. The dependent variable goes on the y-axis, and that represents the force, and the force is measured in a unit called the Newton. Don't really worry so much about the units now. Now, it looks like we need to go up from 0 on the mass. We need to go from 0 up to about 32. So, we probably, to make things easy, we could probably go by 5 z's if you wanted. And we go from 32 here down to 0. So we could probably do 5 z's here. Okay, so there's all my numbering. Now, we're going to make our points, and I'm going to pause the video while I make my points. Okay, I got the points in now. Now, do you see you get this kind of shape that kind of looks like this? And I'm just going to kind of dot it here. And you see that it really rides asymptotically. It rides the y-axis and the x-axis. Do you know what that word means, asymptotically? It gets closer and closer, but it never really touches. And that's true with the y and the x. This is what's called a hyperbola. We see then kind of one lobe. Maybe in a math course you've kind of have talked about some things like this. So that's kind of a double-lobed hyperbola. It's one of the conic sections. So we're kind of seeing just part of it. The top part of it here that represents the positive numbers. Now, what we really are saying here is that, you know, we can't really use y equals mx plus b right at the moment, can we? Because we don't have a line here. But what we can say then, as the y variable is inversely proportional, we can write that, you know, this little proportionality symbol, that's a little alpha, that's our proportionality symbol. We can say then that the y variable is inversely proportional to the x variable. So really, as we're saying, as one variable goes up, the other goes down, and we can really put in our units and our variables that we have here. We could say then their force is inversely proportional to our mass. Now, we don't really have a slope here. The slope is constantly changing, right? So if I put my pin here, the slope is changing. It's not one slope, it's not one line. So typically most books will convert this into an equality, and they'll write a k here, and that k then stands for constant of proportionality. I don't know if that's getting on the page. I hope so. I'm having a hard time getting everything in here. That's called the constant of proportionality, and that's given the symbol k. Does that all kind of make sense? Again, this is just kind of review for math. This is again a type of a graph we see constantly in science. Well, again, the problem is it's not a line. We can't get really a slope. There's no one slope for this. And we really would like to do that because that makes things easier. So I've given you a little bit of room here. We can transform this graph into a line, but we have to do something. So what we've got here is 1 over x. And in math, do you kind of know what we do when we do a 1 over x? There's a special name for that. That's called an inverse. Or a math teacher might use the word reciprocal. Okay, I don't know if that's coming up on the sheet there. There it is. Inverse or reciprocal. So we want to reciprocate this x data, and that's why I left you some room there. Now, on a calculator, if you take a look at something like this, there's a reciprocal key. And that's here. And you've got one on your graphing calculators too. So you would take 0.5, and then you would hit the reciprocal key. And so this first one is 2. The reciprocal of 1 is 1. The reciprocal of 2 is 0.5. The reciprocal of 4 is 0.25. The reciprocal of 8 is 0.125. Okay, now that's we probably don't need to do all the points here, but those are the first 5 points. And so what we want to do is now regraph it. Okay, now our x data now is not the mass, it's 1 over the mass. So it'd be 1 over kilograms. The force here is the same, that doesn't change, and that'll again be in newtons. Okay, so now what we want to do is put our numbers in again, or grid our graph out, and again the y data doesn't really change, so I'm going to go by 5's. But now here it looks like we're going to maybe go from 2 to 0 or so. So I want to maybe kind of spread out things. So maybe what I can say is 0.25, 0.5. Is this getting on there okay? 0.75, 1, 1.25, 1.5, 1.75, and 2. Okay, so I'm just going to kind of leave the camera rolling here while I graph. So we have 232. We have 116. We have 0.58. And we have 0.1252. I'm sorry. 0.1252. It's got something like that. Now, do you see it looks pretty linear? It looks like we make a nice little line. So that's the great thing about what we just did here. We didn't really change the data. We just manipulated mathematically the data to form this into a line here. Now, again, why do we want to do this? Well, because we can use then y equals mx plus b. We can get a slope, right? Now, here's then what we need to do. We need to take then our variables and units that we have here in the problem and convert it here. This is again a math equation. We want to turn it into a science or physics equation. Our y idea is force. Then we have our slope. And then we have our x. But our x is 1 over the mass. So we can write that in the denominator here. And what does it look like the b is? Well, it goes through the origin, doesn't it? So we can make that go away. Now, what we can do is get the slope here, and we've got this point. That's 2 comma 32, and then we can use our 0, 0. Again, the slope then is found m. That's our slope. That's found by taking y2 minus y1 over x2 minus x1. So we've got 32 minus 0. And those units would be newtons. And we have 2 minus 0. So that slope's going to then be equal to 16. And that would be newtons over these units. That would be newtons over 1 over kilograms. Again, I wouldn't worry so much about the units here. So that's kind of how we work on these inverse relationships. We get this, when we graph it, one variable goes up, the other goes down, we get this hyperbola here. That's great, but we really don't like it as much as line graphs because we can't really get a slope. We get this constant of proportionality instead. Now, what we can do is convert this into a line, but we have to do something. We reciprocate the x data. When we reciprocate and regraph, now we get our line. We can use then y equals mx plus b. We can now get the equation. So my equation now is force equals my slope, 16, over my mass. Notice that that's the same really type of equation we had here, right? We had then force equals k over mass. Well, that 16 represents the k, the constant of proportionality. And so here we're able to find the slope, which really represents that constant here. And this is a great thing. Again, this is an indirect or inverse relationship. It's a pretty common relationship we see in physics. We'll talk to you later, kids. Bye.